Good morning. This is the second session of Chapter 4 Vibration Rotation Spectra of Diatomic Molecules. In the last session, we started by representing the rotational and vibrational motion of a molecule around its center of mass by a vibrating rotator. We said that classically the energy of this vibrating rotator is equal to the sum of its rotational energy plus vibrational energy. Then we moved to quantum mechanics. According to quantum mechanics, the energy of this molecule must be quantized. So we replaced the vibrational energy by its quantized value, which depends on nu, and the rotational energy by its quantized value, which depends on J. These values of E rotational and E vibrational were found in chapters 2 and 3. We're using the same values. In this approximation, we were assuming that there is no interaction between rotation and vibration. We're just adding the rotational part and the vibrational part. They do not depend on each other. Now, using the quantized energies, we were able to calculate the wave numbers of spectral lines. We found two groups of these lines, one corresponding to the R branch and one corresponding to the P branch. So, going back to their expressions, so this expression corresponds to the wave numbers of the P branch. You can see it here. This part is related to vibration and this part here is related to rotation. This is the centrifugal distortion correction here. And down here, this is the wave number corresponding to the R branch and as you can see here, this is the vibrational part and this is the rotational part. So using these wave numbers for the P branch and the R branch, we were able to draw a figure for the spectrum. So let's take a look on the spectrum. So this is a spectrum. I'm just giving a conclusion. If we neglect D, which corresponds to the centrifugal distortion, we assume that our rotor is a rigid rotor. So in this case, the difference between the first line in R, which is called R0, it's a transition from 0 to 1, and the first line in P, it's called P1 because it's a transition from 1 to 0. So the difference between them is 4B, where B is the rotational constant. Now the difference between two consecutive lines here is 2B, and any two consecutive lines here is also 2B. This is if we consider the rotor to be rigid, yani D is neglected. Now if D is not neglected, in this case, we see that the difference between the first line in the R branch and the first line in the P branch is equal to 4B minus 8D, it depends on D. And the difference between two consecutive lines also depends on D. In reality, this difference decreases as we go away from the gap. إذا بنرجع على الفورميلا لهون وبنحاول ننقص اثنين ورا بعض، يعني مرة بنحط j مرة j plus 1 وبننقصهم من بعض بنشوف ال distance between اثنين consecutive lines بيطلع إنه it depends on D. وهيدا الفرق بيصغر أكيد كل ما j هي كبرت. بعد في شغلة تانية بننتبه لها كمان إنه اللاينز للبي برانش واللاينز للآر برانش هن symmetrical. يعني إذا بناخد example الأول لاين بالآر برانش بعيد عن هيدا الترم بعيد مسافة 2B minus 4D. أما أول لاين بالبي برانش بعيد عن هيدا الترم نفس المسافة بس من تاني جهة. So it's minus 2B minus 4D. So you can see إنه نفس الشيء في شغلة تانية كمان ننتبه لها إنه the spectral lines of the P branch and the R branch are symmetrical and this appears from their formulas. from the formulas of the wave numbers. So let's take the first line in the R branch. It's equal to this term, let's call it for example x, plus 2b minus 4d. So هو أسود من الx هيدي الكوانتيتي 2b minus 4d. إذا بنجي عند أول line بالp branch it's equal to x, same quantity, minus 2b plus 4d, which is equal to minus 2b minus 4d. So the spectral lines R0, P1 are symmetrical with respect to the position nu bar minus 2 xe nu bar. واحد أزود منه ب 2b minus 4d، واحد أقل منه ب 2b minus 4d. ونفس الشيء إذا أنا بمشي على السبكترال لاينز الباقيين. يعني كمان ال R1 وال P2 will be symmetrical, ال R2 وال P3 will also be symmetrical, etc. بس المشكلة إنه نحنا مش هيدا الشيء اللي لقيناه بالإكسبيرمنت. نحنا بالإكسبيرمنت لقينا إنه كل ما الفريكونسي عليت كل ما المسافة ما بين البيكس عم تصغر. منا سيمتريكال. اللي نحنا وصلنا له لحد هلا هو already good. لقينا 2 branches مثل نحنا متوقعين. في missing line in the middle, it's okay. بس مشكلتنا إنه they are symmetrical. نحنا مش هيك شفنا بالإكسبيرمنت. الإكسبيرمنت the distance between the lines should decrease as the frequency increases. In reality, the bands are not totally symmetric, as you can see here from the figure. So, here is the P branch and here is the R branch. In the R branch, you can see as the frequency increases, the lines become closer. And here the lines become further. The bands show a divergence in the P branch and a convergence in the R branch. Why does this happen? This happens because there is a difference in B between the level nu equals 0 and nu equals 1. Although B is a rotational term, but this B changes with the vibrational level. So there is a relation between vibration and rotation. They are not independent as we have assumed. The independence had led us to obtain a symmetrical spectrum, which is not close to the experimental one. So to be close to the experimental spectrum, we have to consider the interaction model, where there's a combination between rotation and vibration. The B, which is the rotational term, depends on the vibrational level. We will see that the two vibrational levels, 0 and 1, have two different rotational constants. Why does the rotational constant change when we move from one vibrational level to another? One may ask himself, why does that happen? If you remember, B is inversely proportional to I. So B depends on 1 over I. And I is equal to mu R squared. So B is inversely proportional to 1 over R squared. When the vibrational level increases, so the vibration increases, remember that the length of the bond increases. So if the length of the bond increases, which means R will increase, when we go from level 0 to level 1, the length of the bond will increase, and in this case, I will increase, and if I will increase, B must decrease. So we end up by a B for level nu equals 1 smaller than B corresponding to level equals 0. So if we take this into account, we will arrive to a theoretical spectrum very close to the experimental one. Up till now, we have treated the movements of rotation and vibration in a completely independent way. This led to a symmetrical spectrum. In fact, rotation and vibration are interrelated. There's a relation between them. They are not independent. This relation appears in two ways. First, the rotational energy is influenced by the vibrational quantum number nu. So the energy of rotation depends also on nu, a phenomenon called vibration-rotation interaction, which means that the rotational constants B and the centrifugal constant D, these constants which are related to rotation depend on the quantum number nu. They depend on the vibrational level. For each vibrational level, we have different rotational constants. Second, the centrifugal distortion constant, D, can be related to the vibrational frequency, which is nu or nu bar. Okay, so I will explain each one of them in a separate slide. First, let's talk about the vibration-rotation interaction, where the rotational energy is influenced by the vibrational quantum number nu. The rotational energy depends on the vibrational level through the rotational constants B and D. So you can see here that B has an index nu and D here has an index nu. Let's start first talking about B. We all know that B is equal to H over 8 pi squared C mu R squared. B is the rotational constant. B depends on R. It's inversely proportional to R squared. That means when R changes, when the interatomic distance changes, B will change. We know that our molecule is vibrating and rotating at the same time. It has B, it has a rotational constant because it is rotating, and R is also changing because it is vibrating. So what to do in this case? Should we use the value related to the equilibrium position? Simply, the answer is no. We think about taking the average value. Is taking this average value correct? The answer is yes, because the period of vibration is much smaller than the period of rotation. So in a single rotation, the molecule vibrates many times. So because of that, we are able to consider the average value of B. And in this case, B depends on nu. It's equal to H over 8 pi squared C mu, the average of 1 over R squared. So this index nu here says that this B corresponds to certain level nu. So for level 0 it will be 0, for level 1 it will be 1. The average will vary because you know that the interatomic distance will change and the average will change. Now using certain calculations that are not required in this course, BV can be written as B, which is the normal value that we know at the equilibrium position, minus alpha E nu plus half. This is the first correction. Other corrections are much smaller, but this is the most important one. Alpha E is a constant. Alpha E is much smaller than B. And as you can see, alpha E is equal to BV minus BV plus 1. So as we go to higher levels, as nu increase, B will decrease. We have said that before, and it appears clearly from the expression. So كل ما نيو كبرت كل ما البي للنيو راح تصغر. For a certain molecule, HBr molecule, we have for the level 0 it's 8.36, for the level 1 it's 8.134, and alpha E in this case it's equal to B0 minus B1, it's equal to 0.226 centimeter minus 1. Similarly, the centrifugal distortion constant also varies with the vibrational quantum number. Its expression is not developed here in this course also. D nu for a certain level nu is equal to D at the equilibrium position minus delta E nu plus half plus etc. So this is the most important correction. Delta E is much smaller than D. You remember that D is already small. It's already very small. It's 10 to the power minus 4 of B. So we can assume sometimes that this correction is even negligible, and D is approximately constant in all the levels. Okay, so it depends on the molecule, but we can assume that B varies with levels, but D is approximately constant because its correction is very, very, very small. In the previous slide, we have explained the vibration-rotation interaction, how B and D depend on the vibrational quantum number nu. Now in this slide, we're going to talk about the second way that rotation and vibration are interrelated. We're going to see how the molecular constants, precisely the centrifugal distortion, can be related mathematically to the vibrational frequency. So you have seen in chapter 2 this formula which relates D to V. So D is the centrifugal distortion constant, is related to rotation. B, it's the rotational constant, it's also related to rotation. And here there is the vibrational wave number, the vibrational wave number of oscillation of the molecule. So you can see that there's a relation between the centrifugal distortion constant and the vibrational wave number nu bar. So this is a second way of interrelation between rotation and vibration. D depends on a nu bar, not only the quantum number, but also the frequency of vibration or the wave number of the vibration. So remember that the frequency is equal to 1 over 2 pi radical k over mu. So if k increases, the stiffness constant of the bond increases, the nu will increase. So large values of vibrational frequency or large values of vibrational wave number correspond to large values of k. Large values of k means a stiffer connection. In this case, if nu is large or nu bar is large, D will be small and the centrifugal effect is very weak. So the less the connection will stretch under the effect of the centrifugal force. So this is what we can see from this formula. Not only D can be related to nu bar, but also B. So an appropriate calculation based on the Morse potential curves makes it possible to relate alpha E. So this is not developed in the course. We have only just to see the formula, which describes the vibration rotation interaction to the frequency of vibration. So this is alpha E, which appears in the correction of B. It's equal to 6 radical x e nu bar b cube over nu bar minus 6b square over nu bar. So as you can see, both B and D are related to the vibrational wave number. So this is a second way of interrelation between rotation and vibration. Here, a high frequency, so if nu is high, that means the connection is stiff, the connection is rigid, the bond is strong. In this case, alpha E will be smaller and the correction to B in this case will be negligible. Will correspond to a less significant correction, the amplitude of vibration varying little from one quantum number of vibration to another. So in this case, alpha E will be very, very small and simply B nu will be equal approximately to B. So الليفل الأول الثاني الثالث الرابع كلهم راح يكون عندهم تقريبا نفس ال B. So بنستنتج نحن إنه لما يكون البوند ستيف ما بين اثنين atoms بهيدي الحالة الديستورشن كونستانت بيكون approximately negligible وكمان الكوركشن للبي اللي هي الألفا إي كمان بتكون negligible وفينا نعتبر إنه البي is approximately constant in all vibrational levels. أما إذا كان البوند منه كتير stiff فبهيدي الحالة there is a variation in B from one level to the other and D is not negligible. Now let's find the energy of possible transitions in the case of an interaction model, where rotation and vibration are interrelated. So let's consider that B is not constant. Assume B prime is the rotational constant corresponding to level nu equals 0, and B double prime is the rotational constant corresponding to the level nu equals 1. For simplicity here, I will assume that D is constant. Okay, so I will keep it for both levels the same. So in this slide here, we are interested in the rotational part only. Then we will add the vibrational part to get the total rotational vibrational transition. So first, for delta J equals +1, in the case of the R branch, which gives me the lines or the spectral lines with high frequency, delta F is equal to Fj plus 1 minus Fj. So you just have to substitute for F, but just substitute for Bw prime, and here substitute for Fj, and don't forget to write B prime, because B prime and Bw prime are different now. We're assuming that these are the same. So just expand, do your job, and you will get something like this. So this is what we have arrived to, or it can be rearranged in the second way down. Now if delta J is equal to -1, which corresponds to the P branch or the spectral lines with low frequency, delta F is equal to Fj minus 1 minus Fj. This is Fj minus 1, this is Fj. Just take the formulas, substitute instead of B, Bw prime, instead of B, B prime. So remember, we're going from level 0 to level 1. In level 0, the rotational constant is B prime, and in level 1, the rotational constant is Bw prime. Arrange, you will get this, and you can rearrange again to get this shape if you want to expand it in terms of powers of J. To find the wave numbers of spectral lines, we have to add the vibrational transitions to the rotational transitions. So let's start for the P branch. For the P branch, we have a transition from nu equals 0 to nu equals 1, which corresponds to delta nu equals 1. Delta J is equal to -1, which is going from a level J to a level J minus 1. So, and J is the start from J equals 1, as we have said. So the first transition is from J1 to J0. So nu bar P, which are the wave numbers corresponding to the spectral lines of the P branch, it's equal to delta T, it's equal to delta G for a transition from the vibrational level 0 to the vibrational level 1, plus delta F for a transition from the rotational level J to the rotational level J minus 1. So this is the term corresponding to delta G. That's it. This is the vibrational part. And this is the rotational part. You can see the rotational part from the previous slide. So let's go back. Here it is. So this is for delta J equals -1. Delta J equals -1. Just take it, substitute it, and you will get this shape. Now going to our slide, we can find the position of the first line corresponding to the P branch. All we have to do is just substitute for J equals 1. Substituting for J equals 1, here will be 1, and this will be 1, and this will be 1. And we will get nu bar minus 2xe nu bar. We have here minus Bw prime minus B prime plus Bw prime minus B prime plus 4D, and these are cancelled. We are left with minus 2B prime plus 4D. So this is the position of the first line corresponding to the P branch. Now going to the R branch, delta nu is equal to 1, which corresponds to a transition from nu equals 0 to nu equals 1. Delta J is equal to 1, which corresponds to a transition from J to J plus 1. And the first value of J is 0, which corresponds to a transition from J equals 0 to J equals 1. So the wave numbers of spectral lines corresponding to the R branch is equal to delta T equals delta G plus delta F, the vibrational part and the rotational part. This is the vibrational part. It's the same as always, nu bar minus 2xe nu bar. And this is the rotational part. The rotational part was already found in the previous slide. Here it is. So I've just taken it and placed it in the second slide. So I've placed it here. So now, if we want to find the position of the first line corresponding to the R branch, the line just next to the gap, we have to substitute for J0. So راح نحط محل J0، راح نحط محل J0، وهون راح يطلع عندي أنا J0. So this will be 0. So we are left with nu bar minus 2xe nu bar plus 2b double prime, and here we have minus 4d. So this is the position of first line in the R branch. Now let's see the length of the gap. To find the length of the gap, we have to subtract nu bar of R0 minus nu bar of P1. So nu bar of R0 minus nu bar of P1. In the first case, I've neglected D. I've assumed that it's negligible. This correction is negligible. The distortion correction is not important. So if this is the case, this will be 0 and this will be 0. Subtracting these from each other, we are left with this term and with this term. So we are left with 2b double prime plus 2b prime. هلا تذكروا لما كنا انه البي برايم بيساوي البي دبل برايم بيساوي b، طلع معنا الجواب 4b. Okay, when we assume that the two levels in u0 and u1 they have the same b, the answer was 4b. So now it's equal to 2b prime plus 2b double prime. B prime corresponding to the first vibrational level and b double prime corresponding to the second vibrational level. Now if D is not negligible, so let's keep it. Subtract nu bar R of 0 minus nu bar P of 1. So here's a nu bar R of 0 and here's nu bar P of 1. So these are terms that will be cancelled. راح يبقى معي 2B double prime minus minus 2B prime. So it's plus 2B prime. My minus 4D minus 4D, we will get minus 8D. Also remember that when we used to assume that B prime and B double prime are the same, so if B prime is equal to B double prime is equal to B, we end up with 4B minus 8D, which is the same result that we have found when we assumed that there is no variation of B from one vibrational level to the other. Now these two expressions for the P branch and for the R branch can be grouped in a single expression. Let's see how. For the R branch, if we replace J by M minus 1, so all you have to do is just replace J by M minus 1, you will get this expression for delta F. And in the P branch, if you replace J by minus M, you will arrive to this expression. You can see that both expressions are the same. If we go back to previous slide, let's go to slide 18, and let's try to replace, in the case of delta J equals plus 1, which is the R branch, instead of J, we replace M minus 1. So in this case, I'm going to replace it here. So in this case, this will be M minus 1 plus 1, it's M, so this will be M, this will be M plus 1, and this will be M minus 1, and this will be M. So this is the general formula, so it's M, B double prime, M plus 1, minus B prime, M minus 1, minus 4, this is closed here, so minus 4D M cubed. Now let's replace, in the case of delta J equals minus 1, instead of J, I'm going to replace minus M in this formula here. So we will get here minus M, here minus M minus 1, here we have minus M plus 1, and here we have minus M cubed, it's minus 4D M cubed. So just multiply by the minus sign here, so you will get M B double prime M plus 1, and here the minus sign, bring it to the inside, you will get minus B prime M minus 1, close the bracket, minus 4D M cubed. and you can see that the both formulas are the same. Here in the case of R branch, remember that J starts from 0, so values of M start from, remember that M is equal to J plus 1, so if J starts from 0, M starts from 1, يعني the possible values of M are 1, 2, 3, 4, etc., which correspond to the R branch. Now for the P branch, J is equal to minus M, or M equals minus J. The first possible value for J is 1، يعني أول value ل J هي 1، فبهيدي الحالة ال values of M will be minus 1, minus 2, minus 3, minus 4, which gives us the R branch. So this is the difference between R branch and P branch. So to write the general term, the vibrational rotational transition, we have to add the vibrational part plus the rotational part, and you will get something like this. So this is the rotational part, and the vibrational part is simply nu bar minus 2xe nu bar. Add them together, expand to get a polynomial in terms of m. You will see that b is equal to nu bar minus 2xe nu bar, and a is equal to b double prime plus b prime, c is equal to b double prime minus b prime, and d is equal to minus 4d. So a general expression, delta t, will be equal to nu bar minus 2xe nu bar plus b double prime plus b prime m plus b double prime minus b prime m squared minus 4d m cube. هيدي من وين جبناها؟ simply بس هيدي فرطناها وجمعناها مع ال vibrational part اللي هو nu bar minus 2xe nu bar. If we try to plot delta t as function of m, we see that it has the shape of a line. This means that the first two parts are the dominant parts. لأنه هيدول they have an expression of a line. A is the slope, m is the variable, and b is the intersection with the vertical. These two corrections, dm squared and dm cubed, are very, very small, which ensures that b, which corresponds to the vibrational term, and a, which is equal to b double prime plus b prime, are the most important terms that determine the wave number of possible transitions. One last observation about this graph is that as m increases, we can see that the difference in energy between two consecutive spectral lines becomes closer or becomes less. So you can see in comparison with here the difference in energy between two consecutive lines in a P branch is larger than it is in an R branch. This is what was found in the experiment. So this is due to these two terms. هيدا جاي من هيدول اثنين terms، لأنه هيدول الأول اثنين terms لحالهم they give us a straight line. In the case of a straight line, the difference between two consecutive points is constant. But in our case here, cm squared plus dm cube are responsible for this shape of the graph. Imprecise cm squared، بالتحديد اللي هي cm squared. This term here comes from the fact that b prime is different from b double prime. Now how to determine the rotational constants b prime and b double prime? B prime corresponds to the vibrational level nu equals 0, and b double prime corresponds to the vibrational level nu equals 1. First, I'm going to assume that the distortion constant d is negligible, neglect d for simplicity. So how to find b prime? We take two wave numbers that have the same higher state. For example, nu r j minus 1 and nu p j plus 1. Let's take here an example. This line here, which starts from j equals 1 and ends up with j equals 2, and this line here, it starts from j equals 3 and ends up with j equals 2. So this comes from 1 to 2, this comes from 3 to 2. They have the same higher state. نفس الشيء these dotted lines here, this one starts from J1, this is J0, sorry, to J1, and this one starts from J2 and ends up at J equals 1. You can take any two spectral lines that have the same higher state. So they are called new R J minus 1 and the new P J plus 1. In this case, subtract them, find the difference between them, and you will get, going back to the formulas, it's 4B prime J plus half. This transition from J equals 0 to J equals 1 is called, this is R0 واللي حده بالR1 etc. من هيدي الجهة أول واحد which is a transition from 1 to 0 هو هيدا this is P1 هاي transition from 1 to 0 اللي حده transition from 2 to 1 هو ال P2 ويرجع from 3 to 2 هو ال P3 etc. So according to this formula, for example, we can take R0 minus P2 because they both arrive to the same level. R0 arrives to 1 and P2 also arrives to 1. It's equal to 4B prime J plus half. In this case, as you can see, if we according to our formula, J is equal to 1. So it's 1 plus half. Similarly, we can take, for example, R1 minus P3. R1 arrives to 2 and P3 arrives also to 2. So it's equal to 4, B prime is equal to 2 plus half. So that's it. Now the same is done to find B double prime. We choose two spectral lines that have the same lower state. Here I'm taking the new bar R of J and the new P of J. So this is a transition from J to J plus 1, and this corresponds to a transition from J to J minus 1. So they have the same lower state. Here in the previous case, this was a transition from J minus 1 to J, and P is a transition from J plus 1 to J. So they have the same final state J. Here they have the same initial state J. So new bar of R of J minus new P of J will be equal to 4B double prime J plus half. Let's see an example here. Let's take two lines that start from the same level, this one and this one. This starts from 1 and ends up at 2, and this starts from 1 and ends up at 0. So if I subtract them, I will get a value equal to 4B double prime J plus half. This transition corresponds to the spectral line R1, and this transition here corresponds to the spectral line P1. So new bar of R1 minus a new bar of P1 is equal to 4B double prime 1 plus half, where J is the level of the lower state. يعني الليفل اللي هو بلشوا منها اثنيناتهم. اوكي هون J فوق هي level للهاير state اللي وصلوا لها اثنيناتهم. So we can see that if the upper level is the same in the case of the transitions in R and P, يعني عم نوصل لنفس higher state, then the difference between their spectral wave numbers only depends on the properties of the lower level states. So as you can see, in this case, it only depends on B prime. The B prime is the rotational constant corresponding to the vibrational level nu equals 0. If the lower level is the same in the case of transitions in R and P, they are starting from the same rotational level, then the difference between their spectral wave numbers only depends on the properties of the higher level states. So as you can see, the difference of their wave numbers depends on B double prime, which is the rotational constant of the vibrational level nu equals 1. Here, we are going to assume that the centrifuge distortion is not negligible. In addition, we are going to assume that it varies with the vibrational level. So let's call D prime the centrifuge distortion corresponding to the level nu equals 0, and D double prime the centrifuge distortion corresponding to the level nu equals 1. So again, I'm showing the rotational transition for the cases delta J equals +1 and delta J equals -1, but this time I'm keeping D, and dW prime represents the centrifuge distortion for the higher level, and this corresponds to the centrifuge distortion for the lower level. So you can just substitute in the main formula and you will arrive to these two formulas. Now if we want to see the difference between the wave numbers nu of Rj-1 and nu of Pj+1, which have the same higher state as we have done before, so this difference will be 4b prime minus 6d prime j plus half minus 8d prime j plus half cube. So as you can see here again, the difference between these two wave numbers depends on the rotational constants of the lower level only. يعني ما فيها B double prime أو D double prime. It only depends on B prime and D prime, which are the characteristics of the lower vibrational level. Now the difference between nu R of J and nu P of J, which have the same lower state, will be equal to 4b double prime minus 6d double prime j plus half minus 8d double prime j plus half cube. I'm not going to do these, just do them using the formulas up here. Don't forget to add the vibrational term. Anyway, it will be cancelled when we subtract them. But you will arrive to these formulas, and you can see that it depends on the properties of the second vibrational level. On B double prime, D double prime, there is no B prime or D prime. Now for the gap, if we are going to subtract nu R of 0 minus nu P of 1, we will get 2B prime minus 2D prime plus 2B double prime minus 2D double prime. So all I have done, كل اللي عملته إنه هيدي الدلتا F صار معي إياها. أنا معي النيو للR of J هي simply delta J plus delta F. أوكي، ودلتا J بنعرفها نيو بار plus 2x e نيو بار، والدلتا F هيدي. سو هيك بصير معي نيو R of J، ونيو P of J أكيد نيو بار of J بتساوي دلتا G plus دلتا F. الدلتا G معي إياها والدلتا F هيدي هي. سو بتقدروا انتو تعوضوا النمبر اللي بدكم اياه، تعوضوا مرة 0 مرة 1 مرة J مرة J minus 1 J plus 1 اللي بدكم اياه and find these expressions. Now what happens if we replace an atom by its isotope? We all know that the rotational constant B is inversely proportional to mu, and also nu bar is proportional to radical 1 over mu. So both of them depend on the mass or on the reduced mass. So if this mass changes, B must change and the nu bar must change, which leads to an effect of the vibration rotation spectra. So let's take a look on this figure to the right. This is the vibration rotation structure of DCl. We can see that there is a split in the absorption line corresponding to DCl37 and DCl35. The blue lines correspond to DCl35, which is more abundant in nature, and DCl37 are represented in red, which is less abundant in nature. So because there is a difference in the reduced mass, we can see that the position of the spectral lines is shifted a little bit. But because this variation is small, the shift is small. On the other hand, if we take another two molecules, for example, HCl35 and DCl35, D is deuterium, which is hydrogen. In this case, there's a large change in the reduced mass, and in this case, the spectra are in totally different regions. So as you can see, for HCl, it's at 3.46 millimeter, and for DCl, it's at 4.78. So بهيدي الحالة الأولى، هيدي كلها تعتبر هي باند وحدة وفي بقلبها اللاينز الصغار، لأنه التغيير الميو كان كتير صغير، بس شفنا أنه السبكترال لاينز زاحوا شوي. بينما بهيدي الحالة لما تغيير الميو يكون كبير close to a factor of 2، لقينا إنه الباند كلها مطرحها غير. Okay. Now, what is the effect of a changing mu on the rotational term? For B, which is equal to h over 8 pi squared c mu r squared, B, as it appears, is a function of 1 over mu. So if we change an atom by its isotope, then Bi, corresponding to the rotational constant of the isotopic molecule, over B, which is the rotational constant of the usual molecule, it's equal to mu over mu I. The index I corresponds to the isotope we are talking about. For example, if we are taking here C12O and C13O, so let's say B for C13O over B for C12O, it's equal to mu for C12O over mu for C13O. We have already seen that in previous exercises in chapter 2. So the change in the rotational constant between a molecule and its isotopic molecule leads to a change in the energy levels if we compare a molecule with its isotope. And this difference in energy levels leads to a change also in the positions of the spectral lines, as you can see. Now, how does this isotopic effect appear on vibration? You know that nu bar is equal to 1 over 2 pi c radical k over mu. So mu bar is a function of 1 over radical mu. So mu bar I over mu bar is equal to radical mu over mu I, where mu I bar is the constant relative to the isotopic molecule. So we have also seen that in exercises in chapter 3. It can also be shown that Xe for the isotope molecule times mu I bar, it's equal to Xe mu bar, which is equal to mu over mu I. كلنا بنعرف إنه ال Xe بتساوي mu bar على 4 dE. dE هي dissociation energy. So إذا أنا عم بحكي عن isotope رح تكون mu I bar على 4 dE. والdissociation energy ما بتفرق إذا أنا غيرت isotope بالموليكول. So بهيدي الحالة مثل ما شايفين أصلا ال Xe هي بتعتمد على mu bar. فينا نقول إنه ال Xe mu bar is proportional to mu bar square. فكرمال هيك طلع أنا معي الأنسر it's mu over mu I. يعني غيرنا الراديكال.